Today is the 23rd. Okay. Here we go. Any questions? Anything? Okay. Say that again.
Why does B stand for magnetism? Oh, it's true. Yeah, because Topier couldn't explain it because he doesn't know enough German.
He only took 9 semesters.
You said any question. Come on, bro.
You know what?
Wait, did I say I'd give you an answer to these questions? No. I said, hey, any questions? You got a question? I don't have an answer. We got any other questions?
Yes.
Oh, go ahead. Go ahead. WebAssign, go ahead.
This is from the last section of 14.1.
Go ahead.
Here, I'll show you.
We did pretend to so we split all the differences.
Number 4.
Number 4, here we go. This is from WebAssign.
Yep.
It's the double integral. It looks like -1 to 1. Oh, shoot. And -1 to 1, -2 to 2, x squared minus y squared, dy dx. Is that it?
Yep.
Good deal. Let's take a look at this. First of all, what are you finding here when you do this double integral? This is what you're doing. What you're finding is a volume underneath a surface. This surface, z equals x squared minus y squared. That surface is a saddle, believe it or not. You get a saddle point out of that. You get something like this and like this. And it's this way in one direction, that way in another. It's a saddle. Go ahead.
Can you just go over the notation again really quickly? Like if it's dy dx, what's the order for raising integrals?
Okay. The dy dx order means you're going to do the y's first as the variable, okay, and x's as the constant. The x outside will be just the opposite, okay? But at that point, I think it's one of my eyelashes hanging down or something. All right, but anyhow, what? Oh, here it is. Okay. Nah, it's no big deal, just a big spider or something. All right. Yeah, that's what that would be. This is doing the y's first as the variable, x is a constant, and then doing the x's. Okay?
So is that like a, I'm confused on what that shape is.
Over what?
What that shape is.
Oh, yeah, me too. That's a saddle, okay? I agree totally. I can picture the thing, but to draw it, what's that?
It's like an upside down parabola on the x-axis and the right side up on the y.
Yeah, that's what it is.
So is
It's a parabola going this way, and then one going this way on the other side of it is what it is. Actually,
It literally looks like a saddle.
it's a saddle. That's exactly what it looks like. It is a saddle.
So
Okay.
could you draw? Yeah, perfect. All right.
It's a saddle. It's a saddle. You can picture a saddle. That's what it is. Oh, you got it?
I got a saddle.
You got a saddle. There you go. Good enough. That's what it looks like. That's the surface. That's it.
Up on the projector real quick.
Here we go. Now, what are you doing here? You've got this saddle, this surface here, and you're integrating, you're taking the double integral over this region in the xy plane. Now, what's this region in the xy plane? That's a little easier to draw. The y's are going from -2 to 2. The x's are going from -1 to 1. You've got this rectangular region. What you're doing here is finding the volume underneath this saddle over that rectangular region in the xy plane. That's what that double integral is giving you. Okay? That's what it's giving you.
So,
So like,
never mind.
Okay. One other interpretation. There's a totally different interpretation that's possible, though. The other interpretation is, if you've got this as a lamina, okay, in the xy plane. Now, what's a lamina? It's a thin plate in the xy plane that has some mass because it has a density. And if the density function were given as x squared minus y squared, in other words, at a given point, let's say the point, here's a point, 1, 2. What's the density at that point? It would be 1 squared minus 2 squared. That would be a negative density function at that point. It would be a negative 3 density. Every point would have a different density depending on its x and y coordinates. And if you wanted to find the mass of that rectangular lamina, this double integral would give you that mass of that lamina having that density function over that rectangular region. Because what are you doing? With this double integral, you're summing up, you're dividing this up into little squares, okay? And if you consider this a density function, take this square, take this point, say, you're getting the mass of that square. What's the mass of a square? It's its area, which would be delta x, delta y, times the density function at one of those given points. And if you sum them all up, you're going to get a Riemann sum in terms of x's and y's. And if you let the number of them go to infinity, you're going to get this double integral. So this double integral is an area under a surface over the rectangular region, or the mass of this rectangular region with that density function. There's two possible interpretations of that same thing. Go ahead, Lee.
It's like that square region you're creating in the xy plane, 4 by 2. And then it's going to make a height, which is going to be the z value from those points, right?
That's correct.
And then the volume is like a cup. And the amount of
Yeah.
the cup that's filled with the graph is what you're solving.
That's correct. That is correct. That is good. That is good. Good deal. Let's do it. Let's do this. Now, how do you do that integral? Let's see. We'll do the inside one first in terms of y's. That means x is a constant. And when we integrate x squared with respect to y, it's going to be x squared y. And when we integrate y squared with respect to y, that's going to be a y cubed over 3. And the limits of integration are negative 2 to 2. And we still have our x's to go. Okay? So you do the innermost one first. Substitute in 2 for the y, we'll get 2x squared minus 8 thirds minus, now substitute in negative 2, we're going to get a negative 2y squared, x squared rather, minus, and when you put in negative 2, it's negative 8 thirds, but it's minus, so that's a plus 8 thirds. And we got dx, and hopefully my signs are all right here. I guess they are. So we end up with 2x squared minus plus 2 more x squared, so we get 4x squared minus 16 thirds. Okay, and now integrate with respect to x to get 4x cubed over 3 minus 16 thirds x. What do you think, Omar?
Yeah, that's what I've done so far.
Really? All right. Uh-oh, and you got it wrong? Uh-oh. That's not good. All right, put in a 1, we get 4 thirds minus 16 thirds minus, now let's put in a negative 1, we're going to get a negative 4 thirds minus a negative 16 thirds, which would be plus 16 thirds. Now we're going to get 4 minus, it's negative 12 thirds, that's negative 4 minus 4. Okay, we get 12 thirds or 4, and that's a negative 8. Is that what you got?
I solved it the first time I got negative 8. Second time I got negative 8 thirds, but they both got marked wrong. Maybe it was a positive 8. I got my signs wrong.
All right, I don't know. It should be negative 8. Should be negative 8. Should be negative 8. We could verify this. Actually, Dan could verify this with a double integral, because Mathematica does the double integrals rather easily, I must say. So, could you do that, Dan? This double integral? Well, I'm thinking now the answer should be 0, and these things just cancel out, but maybe, all right, well,
I'm feeling
I know, me too, but let's see what Mathematica says.
although, no, it's not just 0. No, that would be. Wouldn't that be negative? Wouldn't that be like negative 24 or something? No.
I got negative 8 the second time I tried.
Wait, you get negative 4 minus
Over.
No, it'd be
12.
positive.
What do you
It'd
got?
be negative 8.
Negative 8. Yeah, baby. Should be negative 8. Thank you, Dan. All right, any others? Somebody else had one. Brandon, you had another one? You have one? No? Brandon.
Wait, what are you doing?
I'm doing nothing. I'm just practicing my beats. All right. Okay, you guys ready to go on? Let's go on. Here's what we have to do. Let's revisit the paraboloid problem we were doing the other day, where z is equal to 40, I believe. I had 40 minus x squared minus y squared. Something like that. Oh, was it 10 only? Okay, that's all right. It doesn't even matter. Let's do 10. Let's take a look at this. Oh, gosh. Here's what we have. And what we did, we found the volume underneath this surface over a triangular region in the xy plane. Okay? And it wasn't that bad. We used our rectangular coordinate system, and it wasn't too bad at all. Let's suppose, however, the real problem is to find the volume underneath this surface over the circular region in the xy plane. This is the actual problem that had to be solved for that entertainment tent that I forget what it was called now. It wasn't called it was a special name they gave to the thing. But anyhow, whatever it was, and we want to find the volume underneath this thing. Well, let's set it up as a double integral over our rectangular coordinate system, and let's see what we have here. First of all, when z is equal to 0, we get x squared plus y squared equals 10. So this circle in the xy plane is going to be x squared plus y squared equals 10. So this point here would be the square root of 10, 0, and 0 square root of 10. Okay? So we're going to take the volume underneath this surface over the circular region. Well, let's set it up. Let's do it. Volume is equal to. I'm going to use the symmetry of the situation to find the volume in the first quadrant and multiply by 4. Okay? So I'm going to say 4 times the double integral. We're going to integrate underneath this surface. We're going to take dy dx. Now, where are the y's going to go? The y's are going to go from here, the bottom, at 0, until we hit the graph of the circle. The equation of that circle is the square root of 10 minus x squared. That'll be the upper limit on that integral. Y's are going to go from 0 until we hit the function. The x's are going to go from 0 until the square root of 10. Okay. The innermost limits are going to be in terms of the outermost variable. These will be in terms of x, but this one is 0 to when we hit square root of 10 minus x squared. All right. That integral will give us the exact volume. Well, what's the problem with this? The problem with this is if you do this for one step and do this integral, and have to substitute this in, This turns out to be a nasty integral after you do the substitution. Watch what happens. You end up with 4. You get 10 square root of 10 minus x squared minus x squared square root of 10 minus x squared minus this thing cubed, which is 10 minus x squared times the square root of 10 minus x squared over 3 dx. Now that's not as bad as it looks because you get a 10 times the square root and then you have a minus 10/3 of them, so you can at least combine those. They don't cancel.
I'm confused.
All right, go ahead.
Oh, no, never mind. Got it. Figured it out.
Okay, good deal. Anybody else set on this? Go ahead.
For the limits of, like it's 0 to square root of 10, I have to get square root of 10.
Square root of 10 is this point right here. So my x's are going to go from left to right, and the x limits will be constants.
0 for the other one.
Yeah. If you plug in, yeah, exactly. Plug in 0. Okay, this is a nasty integral. This integral here is pretty nasty. How would you do this integral right here? What? Dan? That's a good answer. Dan, yeah. All right. Another way, if you're at home and Dan's not looking in your closet, would be to...
Email Dan.
Another way would be, the actual way would be to do a trig substitution, let x equal the square root of 10 sine theta. Or you could recognize this is an area of a circle and you could do the integral without doing the integral by seeing, oh, that's an area under a certain region. We could do it that way.
Yeah,
But this one is, but this one is nasty here. You'd have to do a substitution, x equals square root of 10 sine theta, and it'd have to be out here too. You'd end up with a sine squared here. You'd end up with a sine squared in there. And then you'd have to take out 1 minus sine squared would be a cosine squared. You could probably do it, but it's nasty. There is a better way. Here's the better way. This could be done, but it's not nice. The better way is to do the following. We need another coordinate system to deal with this. That other coordinate system we need is our cylindrical coordinate system in 3 space, where it's called our polar system in 2 space, in 3 space, where it's called a cylindrical coordinate system, which we looked at a little while ago, a couple chapters ago. Okay? Let's go back over that again. All right? Cylindrical coordinate system. Okay? Yes!
I had a really cool side.
Go
Last
ahead.
night on Jeopardy,
Oh.
they were like, what's the surface where every point on the surface is equidistant from the center?
Oh, really? They had that on Jeopardy today? Oh, wow.
Is a champion round.
That was, really?
Yeah.
Wow. They all get it? Or somebody got it at least.
My guy got it.
Yeah.
My boy Alex.
Wow, cool. Pretty good. Cylindrical coordinates are r's, thetas, and z's. Okay. What is this? This is our polar coordinate system extended to 3 space. The z's in the cylindrical coordinates are the same z's that we have in rectangular. It's the height above the xy plane. R's and thetas are the same r's and thetas that we have in polar coordinates. Okay? So, what we're going to do is change this problem to a problem in cylindrical coordinates. Okay? In general, when we have circular regions in the xy plane that we're dealing with, like we are here, you're better off going to a cylindrical coordinate system. And the reason you're better off going to a cylindrical coordinate system is, what's the equation of this circle in polar coordinates? What's the equation of that circle right here? And what is it?
X squared plus y squared.
That's what it is in rectangular.
R equals blank,
R equals
whatever.
square root of 10. That is correct. The radius. That's exactly right. It's r equals the square root of 10, a constant. That difference makes all the difference in the world. Because now we can do the integral, but the limits of integration are not these square root things here that we have up here, but a constant. And that makes a huge difference in doing the integral. But here's what we have to do. We have to be able to do this in terms of cylindrical coordinates. This dy dx is in terms of a rectangular coordinate system. Where did we get dy dx? Well, we got dy dx by taking this area in the xy plane, dividing it up into little squares, the area of which was a delta x times a delta y, which became our dx dy when we took the limit as the number of them went to infinity. We have to do the same thing for polar coordinates. Here's what we're going to have to do. We have to do this. We have to take this r in terms of theta, and we have to get a piece of this area in terms of delta r's and delta thetas instead of delta x's and delta y's. And that's exactly what we're going to do. This distance here is delta r. What we need to do is get that area in terms of delta r's and delta thetas, just like we did with rectangular when we have delta x's and delta y's. So here's the deal. Let's take a midpoint here, and let's say that this distance is r sub I, which is some function of theta. Okay? I'm going to go to here. And I'm going to call this r sub I. Okay? That's my function. I need an expression for this area right here. Well, what is that area? That area is the difference in the area of two sectors. Okay? That piece of area, that a sub I, bless you, is approximately equal to the area of the outside sector minus the area of the inside sector. Okay, you with me? This little piece right here is delta r over 2. This little piece here is also, it's getting a little crowded in here, delta r over 2. So what I'm doing is taking r to the midpoint. The rest of the way would be a delta r over 2. Going back the other way is delta r over 2 as well. Okay. What's the area of the outside sector, this sector out here? What's the area of a sector in general, of a circle, whose central angle is delta theta? What's the area of a sector of a circle whose central angle is delta theta, whose radius is r?
Theta times r.
What is it?
Theta times r.
No. No, I want the area of a sector of a circle, piece of pie. You know the angle here, the central angle is the delta theta in our case, and you know the radius of the circle is, say, r.
1/2 theta r squared?
1/2 theta r squared. 1/2 theta r squared. Not quite, but close. What's the area of the whole circle? Pi r squared. What part of the circle do we have? We have a delta theta over 2 pi. So our pi's will cancel, so we get 1/2 delta theta r squared. Oh, that's all it was. All right, you just didn't have the delta, you had the theta. All right. All right, so here's what we got. Outside sector, its area is delta theta over 2 pi. What is that? That's the fractional part of the circle we're talking about, okay? If delta theta is like, let me do it in degrees here, 30 degrees, we're talking 1/12 of the circle. 30 degrees over 360 degrees, 1/12. This is the fractional part of the circle we're talking about, okay? Times the area of the whole circle, which would be pi r squared. Now, what's r in our case here, though? It's this r plus delta r over 2 squared. The function r is going out to the middle, and then I have this additional amount to get to the end for the outside sector. So we have delta theta, our central angle, over 2 pi, that's the fractional part of the circle, times pi r squared, that's the area of that whole circle, having that outside arc, okay? Doing the outside part. All right, is that reasonable there? Is it reasonable? Really? Oh. Minus the inside guy. The inside guy is delta theta over 2 pi, a fractional part of the circle, times pi, times r minus delta r over 2 squared. Wow. That's this right here. That's that little piece of area that we're talking about. In rectangular, it was a delta x, delta y. In polar and cylindrical, or in polar right now, it's going to be this mess, but this mess will simplify. Pi's cancel. I can factor out a delta theta over 2. And I'm going to have this squared. Twice the product, so the 2's cancel. Minus this guy. Middle term is a minus, so this becomes a plus. This is a plus, it becomes minus. That's over 4. All right, check that out, okay? I'm going to factor out a delta theta over 2 out front. I'm going to square this thing, which is r squared. The middle term is twice the product. The last is the delta r squared over 4, minus, and then I have to do this one here. Okay, so it's r squared. The middle term is minus, so it becomes a plus, because the whole thing is being subtracted. The constant is a plus, so it becomes a minus. Okay? So, what do we got? That piece of area is delta theta over 2. R squares cancel. Delta r squared is over 4 cancel. I get 2r delta r. Then the 2's cancel. What do I end up with? This piece of area is approximately r delta theta. That plays the same role that a delta y, delta x plays in our rectangular coordinate system. It's a little piece of that area. We're summing up all those little pieces and getting that Riemann sum, but this time in terms of r's and thetas. So here's what we have.
I'm confused on why everything canceled there.
Oh, what? What happened?
How does that work out so nicely?
How did it work out like that?
I see it. All right. I see
Do you see it? You sure? What I did, this is a minus, so I had to subtract this square from that square. All right, check it out. Check it out. You got it, Tim? Tim has it, so I'm going on, so that's it. All right?
Yeah.
All right.
That's what it's got to be.
That's true. Any questions on that? It's an algebra thing there and there. There's a bunch of it, though. It's a little messy, but
Do this every time, or is this just a format we get? And then
you will never need to do this in your lifetime, okay? I am doing it to show you that what comes up with the cylindrical coordinate systems makes sense. This is where it comes from. If you pitch the tent, you still don't have to do this because I'm going to give you the result. It's the results that matter, okay? You ready? The result. I want to make sure everybody's okay. All right. Here we go. I'm going to give you this. In rectangular, we have volumes that are double integrals of our functions dy dx, dx dy, doesn't matter, where the y's are going to be from one function of x to another, and the x's will go from one constant to another. That's in rectangular. We've got a surface over some region, okay? That region is defined here. These, the y's are going from g1 of x to g2 of x, x's from x sub naught to x sub 1. In cylindrical, the double integral is a function in terms of r's and thetas. And instead of dy dx, we're going to have an r dr d theta. And where does that come from? It comes right from here. Okay? That's what that piece of area is. That piece of area becomes our r dr d theta. our limits are going to go from some function of theta to another. Theta limits are going to go from some theta to another. Okay? Let's take a look at the paraboloid problem. Okay? Let's find the exact volume underneath that paraboloid. Here we go. In rectangular, we had 10 minus x squared minus y squared. We had this. Okay, then this circle, the circular base, we had this. This is our region in the xy plane. Okay. In rectangular coordinates, we had that. Okay? All right. We set up the integral in rectangular. We started doing it and saw that it was nasty integral to do. Very nasty. Okay? Let's do the thing now in cylindrical coordinates. Let's start with the volume that we had before. We had the volume that was equal to the double integral of our surface, 10 minus x squared minus y squared, dy dx. We said the y's are going to go from, and we had 4 times it, 0 to the square root of 10 minus x squared. From 0 to the function. The x's will go from 0 to the square root of 10. That's what we had in rectangular. Let's do it in cylindrical. In cylindrical, 4 times. Now, what happens to our surface? We've got, this surface is z equals 10 minus x squared minus y squared. What are we going to have to do? We're going to have to change it to cylindrical coordinate system. What does 10 minus x squared minus y squared become in cylindrical coordinates? Instead of z equals 10 minus x squared minus y squared, we're going to have z equals what?
10 minus r sine squared minus r cosine squared?
Yes, but when you do that and simplify it, thank you, r squared is correct. That away, Jane-ish. Okay? You'll end up with 10 minus r squared sine squared plus r squared cosine squared, which is r squared because sine squared plus cosine squared is equal to 1.
The 1.
That's a mouthful.
Oh, yeah, over here. Oh, I thought you were talking. Oh,
No.
okay, I thought you were talking about Ed. And
Nah, Ed didn't do anything.
Ed never does anything wrong. I've seen his physics stuff.
all right, anyhow, this becomes 10 minus r squared. Another way to look at it, 10 minus the quantity x squared plus y squared, and x squared plus y squared is r squared. Now, the dy dx becomes what? R dr d theta. Okay?
So, because of the way the proof works out and because there's cylindrical coordinates, does the order matter now?
The order still doesn't matter. But I got to tell you, I can't think of a single example where we'll take the thetas before the r's. The y's before the x's and the x's before the y sometimes occurs because it's easier one way. But all the time, r's come before thetas.
Ooh, is that r dr?
That's r dr d theta.
Oh, okay.
That's an r.
Yeah.
Now, what about your limits of integration? Back here, the y's went from bottom to top. R's are going to go from center out. That's how r's go. R is the distance from the origin, right? That r. Okay. So it's going to go 0 to square root of 10. That's correct. Okay. After all, what's the function is r equals the square root of 10. Okay, that is that function in cylindrical coordinates. So r's will go from 0 to the center out till we hit the graph, square root of 10. Where are the thetas going to go? 0 to pi over 2 is totally correct. This integral is going to give us the exact volume under that surface. Let's do it. You get 10r. we're going to integrate that 10r squared over 2. You have an r cubed, that's r to the 4th over 4. 0 to the square root of 10, d theta. Substitute in. Okay. What's that? Okay. That's equal to 4 times the integral 0 to pi over 2. Square root of 10 here gives me 10. That gives me 50. Square root of 10 to the 4th gives me a 25. I end up with 25 d theta. And it's just amazing. It comes out so simple. That's equal to 100. The integral of d theta is theta. We end up with 50 pi. The exact volume underneath that paraboloid is 50 pi cubic units. Okay? That's exact volume underneath that thing. Okay. Now, I've got time to do one more thing. All right, you ready? Is this okay? All right, what I want to do is derive the volume of a sphere. Okay? We're going to derive that formula for the volume of a sphere. Let's do it.
Can I see that last part just for a second?
Oh, yeah. Yes. Oh, okay.
Okay, I'm all set.
It's not okay.
Okay. You sure? Okay. Let's derive the volume of a sphere. Here we go. Do. Let's take a sphere. Tell you what, I'm going to take the upper part here, hemisphere. Actually, what I'm going to do is take 1/8 of the sphere and multiply by 8. The equation of this sphere is x squared plus y squared plus z squared equals r squared. We're talking about a sphere of radius r. Okay. And what we're going to do is take a look at it over this first quadrant here in the xy plane. We're going to take 1/8 of the sphere. Okay? So here we go. The volume is equal to 8 times. I'm going to set it up in rectangular first, and then we'll do it in cylindrical. Okay? So, we got the double integral. Our surface is square root of r squared minus x squared minus y squared dy dx. The y's are going to go, now the equation of this circle is x squared plus y squared equals r squared. Okay. So the y's are going to go from 0 until you hit the function, which is the square root of r squared minus x squared. Okay, that's the equation. The equation of that, when you solve for y, is going to be the square root of r squared minus x squared. And the x's are going to go from 0 to r. That integral, that double integral, will give us the exact volume of that sphere. Problem is, this integral is very nasty. This integral right here, that square root of r squared minus x squared minus y squared dy, is nasty. It's a trig substitution. Again, and you don't want to even, you don't even want to do that. Let's do it. What's that?
I definitely don't.
Yeah, I don't either. I don't either. Instead, we're going to change it to cylindrical coordinates. Okay? Let's change it to cylindrical coordinates. The equation of the sphere is z squared equals capital R squared minus x squared minus y squared, or z equals the square root of r squared minus x squared minus y squared. Okay, that's where this came from. But now I want it in cylindrical coordinates. So what's the equation of my sphere in cylindrical coordinates?
R squared minus R squared.
Yes, it is. I'm sorry. Yes, it is. All right?
Way too excited.
I know. Yeah.
No, it's okay.
Good deal. That's the equation of that sphere in cylindrical coordinates. Replace that x squared. If you take the minus out front, so to speak, you get x squared plus y squared in parentheses, which you replace with r squared. Okay? And then what's the rest of it? Instead of dy dx, we have r dr d theta. And thank goodness for this r here, because it'll serve as our du part when we do the integral. We don't have to do any trig substitution. In addition to that, where's r going? R is going to go from 0 to, what's the outer limit of little r? Big R, yes. It's going to go from here to here. The equation of that circle is, good job. And theta is going to go from where to where? 0 to pi over 2. When we do this integral, we ought to get the volume of a sphere of radius r. That's what should happen. Now, what's the answer should be? What's the volume of a sphere? 4/3 pi r cubed. All right, let's see what happens. Let's do it. Do the integral here. Now, this is a u to the n form where u is big R squared minus little r squared. The du part is a negative 2r dr. I'm going to have to multiply by a negative 2 here and a negative 1/2 out here. Bless you. Okay? In order to get my du part. That will give me r squared minus r squared to the 1/2. When I integrate it, it will be 3/2 times 2/3. And I'm going to go from 0 to r d theta. All right, you've got to check that out. Here's what I've done. My u is big R squared minus little r squared. The du is a negative 2r dr. I have an r, but I need negative 2 of them. So I multiply by negative 2 here and negative 1/2 outside. That gives me the du part that I need. This becomes a u to the 1/2 du integral, which is u to the 3/2 divided by 3/2, which is times 2/3. Okay? That's what the integral is. So what do we have here? The 2's will cancel. I've got a negative 8/3 integral from 0 to pi over 2. When I substitute in big R for little r, I end up with 0 minus, this will change that to a plus, substitute in 0, I'll get big R squared to the 3/2, which is big R cubed. Check that out. Make sure that's okay. Okay? What do you think, Dave? It's okay? Okay, here we go.
Is that supposed to be a positive integral?
That's going to be positive now because when I substitute in big R, I get a 0. And then it's minus, and then substitute in the 0. And that minus will change this minus into a plus. Okay? Now, integrate r cubed d theta. I'm going to have 8/3 r cubed. The integral of d theta is theta. 0 to pi over 2. Okay. I end up with 8/3 r cubed theta, which is pi over 2. I end up with, 2 goes here once and in here 4 times. I end up with 4/3 pi r cubed. Done. End. Feels good, you know? Feels good.
Wow.
All right. That's the volume of a sphere derived with a double integral as the volume underneath that surface over that circular region. So, here's what we do on Monday. Monday we'll do density function and look at the centroid of laminas of varying density. Very similar to what we just did here. Okay, very similar to that. Tuesday, we're going to do triple integrals. We'll start our triple integrals. Wednesday is going to be a help day. I'm not going to do anything new on Wednesday. I'm going to be here. But if you need help in doing any of the problems, web assigned problems, any problems at all, I can help you. I'm not doing anything new. Okay? On Wednesday. Thursday, Friday, we're off. Week after, Monday, we're going to finish up on triple integrals because triple integrals, really, they sound tough, but they're not really. We're going to have our next test Thursday of the week we come back after Thanksgiving. Okay? Thursday. That gives us enough time to finish up the last chapter. We only do a couple sections of it and to have our last test. What's that? After that Thursday will be our last test. We'll have one more test after that because we have a half a chapter to do. Ready? No. We have a separate final that's on everything.
Is that the same format as the other?
25 multiple choice questions. Questions are very similar to those other test questions too. Very similar.
Will we do a roadmap for that now?
What's that?
Will we do a roadmap for that?
Yes, we will. I'm going to tell you what to expect.
That's probably annoy you a lot, don't it?
Well, I'm sure you don't want to.
You don't annoy me at all. Not at all. You don't annoy me.